Good morning, everybody. Did you miss me? No. Don't answer that question. Don't answer that question. We're going to really pick up the pace. Today, we're going to do Coulomb's law, which is talking about forces on charges. We're going to introduce you to kind of how quizzes, Mr. Balogh's weird way of doing quizzes, and then we're going to try and get into electric field, and we'll see how far we get. The goal is to be done with chapter 18 by today. Maybe. Review. Last time on Tuesday, we talked about the nature of charge, and my demo up here did not work correctly. Well, I found a different electroscope this time, right? So let's see what happens, right? If I try to rub the rod and just hold. Oh, it did a little bit. I swear this worked 10 minutes ago. Oh, there it goes, right? You see it moving even though I haven't touched the top. It'll reset back to its 0 point. And then I can influence it, right? So we can cause that polarization to happen whether we're touching or transferring the charge or not, right? Which just shows that there's this influence across space without having to touch it. Well, continuing the parade of old white guys, Charles Coulomb decided to figure out kind of just the mathematical relationship between everything that's going on here. And what it boiled down to was identifying the amount of force that charges can exert on each other. Now again, we know the rules, right? What happens if you have, like, say, two positive charges? They repel, right? And if you have positive and negative? Attract. And then so we know those rules. So what Coulomb did is he said, look, he did some experiments and things like that, did some observations. He discovered that if you've got two charges, okay, that are next to each other, and your book is pretty careful, uses absolute values around these charge symbols. We use Q as a symbol for charge in physics, and if it's little q, generally that just means it's some variable amount of charge somewhere. You'll see me write big Q sometimes. I'll get into that a little bit later. But Q in general, whether it's capital or small, lowercase, is charge. He discovered that you have to multiply the amounts of charge together, right? And then it depended on the distance between those two charges squared. In physics, we use R as a distance. And I know you guys think, immediately as soon as I write down R, what do you think? Radius, okay? Which is perfectly valid because sometimes the distance we're talking about is a radius. But at other times, it's just the distance between things, right? So if you want to put like a D in there instead, but your book uses R, I'll stick with R. It's the distance between the charges squared. But if you take, let's see, unit-wise, this would be a Coulomb squared over a meter squared, right? Well, does anybody remember what the units of force are? Newtons, fig newtons, right? Okay. So this isn't a Newton. Coulomb squared times a Newton, divided by a meter squared is not a Newton. So in order to fix that, we need to stick a constant in front of this equation. Now the constant, you hope it's a constant, and spoiler alert, it is. It doesn't matter where in the universe we go. This number, okay, is the constant that sets the amount of force between charges. And now we've got to fix the units, right? So like, what do the units of this thing have to be? Well, we know that the force has to come out in newtons, right? We know this side has to be newtons. So what we need this K constant to do right here is to cancel out a charge squared and cancel out a meter squared and end up with a Newton, okay? And so if we kind of rearrange some things, right, and do some hocus pocus that you don't need to worry about, in the end, all that matters is that this constant is a Newton times a meter over a Coulomb squared. That should get us where we need to be, okay, for the force constant. That doesn't seem right. My notes seem wrong for a second. I need a meter squared. This needs to be a meter squared. There we go. All right. So what kind of number is that constant there? Like is it a big number? Is it a small number? What do you think? Looks like a pretty big number, doesn't it? Quiz time, or not a quiz. Check your memory. What's 10 to the 9? Giga. Good job, right? Okay. So this, whatever this is a giganewton meter squared per coulomb squared, right? This is a huge number. And believe it or not, you've actually seen an equation very much like this one in Physics 2a. Does anybody recognize it a little bit? It didn't have charge in it. It was gravitational force, wasn't it? Gravitational force due to gravity, right? It had a constant, big G, and then it had a mass 1, a mass 2, and then there was also a distance squared there. Let's talk about the distance squared real quick. If I take two charges, okay, and I put them, say, 1 meter apart from each other, and then I double the distance between them, does the force go up or down, first of all? Goes down, right? It's in the denominator, it's inversely proportional, so it's going to get weaker, okay? But the question is, how much weaker does it get? I've doubled the distance. So whatever's going on with the charges, right, I now double my distance in the denominator, but it's a doubling of distance squared. So what does this turn out to be? It's fourth, right? So this is called the inverse square law, right? If I double the distance, the force goes down, but it doesn't go down by double, it goes down by 4. What happens if I triple the distance? It goes down by 3 squared, 9. What happens if I quadruple the distance or go 4 times as far? It goes as a 16th, right? So this is called the inverse square law. And last semester, it was mostly gravity that did this for you. But we got it now in electricity. Light does this, the intensity of light. As you come off of a light bulb or something, the intensity of Wi-Fi, okay, as you get further and further away from it, goes down. But it goes down as the inverse square. If you double the distance, quadruple, so on and so forth. All right, so it's one of those things that physicists look at. We go, wow, the universe actually is kind of an organized place, right? Like this idea of intensity and strength going as an inverse square. That's pretty nice. But does anybody remember what the value was for big G? Like maybe not even just the actual number, but like was it a big number? Was it a small number? The big G is not named correctly, right? Because we have little g and we have big G, but it turned out that big G was really a really tiny number. It was, I think it was like 6.67 times 10 to the minus 11, right? It's like a number so small it might as well be 0, but it's not, annoyingly. And so big G, right, small number, okay, K, the electric force constant, is a huge number. So what's stronger? The gravitational force acting on you right now? Let's make this more equal. What's stronger? The gravitational force acting, say, on 2 masses that are next to each other, like 1 meter apart from each other, or the electric force between 2 charges that are 1 meter apart from each other? Electric force? I mean, electric force has the bigger constant, right? Okay, let's put it in different terms. Let's say, okay, we're not going to actually do this, but let's go for a field trip, right? And we're going to go for a field trip, and we're going to go to the top floor of the science building, okay? And I'm going to start throwing you off one at a time, okay? I want you to tell me which is stronger, the gravitational pull on you or the electromagnetic repulsion between the atoms in your body and the atoms in the concrete. In other words, who wins? Gravity or the electromagnetic force? Gravity? If gravity was the winner in that situation, what would happen? So we've got the concrete and your atoms, right? Okay, pushing apart, and you got gravity pulling you in. If gravity were to win, what would happen as you approach the concrete? You would fall through the concrete. Okay? The electromagnetic repulsion between the electrons in your body and the electrons in the concrete, the protons in your body and the protons in the concrete, is way stronger. Like way stronger. Like 10 to the 30 times stronger than the force of gravity. And yet, we wander around thinking like gravity's a big deal, blah, 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 right? Why do we think gravity's a big deal? You had to wake up this morning, right? And when you were waking up this morning, was there a little bit of you that was just like, oh, please, gravity this way today? Right? It feels strong, doesn't it? Anybody that's tripped, especially in front of somebody you're trying to impress, right, knows just how weighty gravity can feel, both physically and emotionally, right? But we don't think about electricity, like Coulomb's law, this basic law that governs the force between all charges in the universe, because it's kind of like always there all the time. What's winning right now, gravity or the electromagnetic repulsion between the floor and me? It's the electromagnetic Gravity's winning? No, if gravity were winning, what would be happening? I'd be sinking through the floor, right? The floor wouldn't be as strong as gravity. Do you want to see me overcome gravity? I've refined this over many decades of life and specialized training and all that kind of stuff, right? Do not try this unless you have at least a master's degree in physics, okay? You ready? Yeah. Pretty amazing, huh? Okay. So what happened there? I pushed off the floor with more force than gravity was pulling down on me. How do you know? Because I went up. My acceleration was in the upwards direction, right? My net force was in the upwards direction. So what's another way to think about this? Back in Physics 2A, we tortured you with a lot of different forces, didn't we? Let's see if we can remember some of this. Normal force? Tension? Frictional forces? Right? Where does the normal force come from? You mean Dr. Kerfoot never taught you? Well, he wasn't supposed to. He taught you about the normal force. He taught you that the normal force happens whenever two objects come into contact with each other. But did he ever tell you, like, why it happens? Where it comes from? What the fundamental force is that makes it happen?
Isn't it like basically?
It's not gravity. It's Coulomb's law. Which you're staring at right there is responsible for the normal force. It's just instead of like trying to apply it to every single little electron between like, my hands and the table, we just tie it all together as one big normal force, okay? Tension, where does tension come from? Coulomb's law. Tension in strings, what holds the string together? The connection between the electrons and the protons. Friction. Where does friction come from? The answer is not gravity. Coulomb's law. This right here is way more fundamental than gravity. Gravity is kind of boring, right? In terms of what's happening right now with you. You are experiencing Coulomb's law right now because the chair is holding your rear end up. The table. What is the table made of? Plastic, maybe, probably not wood, right? A little bit of metal, okay? What is it made of? Atoms. What are atoms? Protons and neutrons and electrons. What takes up most of an atom? Not air. Air is a molecule, that's bigger. That's a glass. That's half of the glass with water in it. Is it half empty or is it half full? Neither. It's 99.99999% empty. Why? Because atoms are mostly empty space. What exists between a proton and an electron? Well, as an Italian, I have to admit that it's olive oil. Olive oil is what holds the universe together. But in a scientific sense, right, what is there? Nothing. So why does it feel so hard? Because of Coulomb's law. Anatomy and bio majors. How is it that I am able to feel? What is it? What's the structure in your fingertips that lets your brain know something's happened? There's a nerve ending, right? Okay? There's a nerve ending that's responsible for going, oh, pressure, right? And your brain goes, ah, pressure, right? It's charges, isn't it? Yeah. And how do charges know how to move and push on each other? Coulomb's law is everything. It's like the most fundamental force that everybody experiences and nobody even realizes is hiding there, right? Okay? So how do we deal with it? How do we use it? So it gets really complicated really fast, right? Nerve conduction, all that kind of stuff. Pretty complicated process. What we're going to do is we're going to really take a sort of a simplified look at this. And it's not because you're stupid. It's because we want you to be able to go on in life and do good things, right? If I spent a lot of time teaching you all the actual physics that was going on with Coulomb's law, we'd be here for the whole semester. That's called Physics 4B, okay? So what we want to do is we want to look very sort of narrowly and simply at an example of how we deal or work with, right, the equation that's sitting right there. So the first thing off the bat that we kind of need to accept, we're just going to let it flow into us and over us and through us, and it's going to be okay. What is a force? Is it a vector, a scalar, or an elephant? It's a vector, right? It's a vector. Okay. So let's let's just I don't even remember what that quiz was. What's that quiz? Oh, that's that quiz. Let's see if we can't jumpstart our memory of vectors with a quiz. We did quiz in here before, right? We did the cat one. So get your quiz sheets out. (18.3, 18.4, 2 points each. Remember, fill out both boxes, right? 18.3, 18.4, out of 2. The first box is just for you doing it by yourself, and then the second box is for doing it as a group when I tell you it's okay to do that, okay? So 18.3, 18.4, out of 2 points. I can remind you later, but here is the quiz question. After today, quizzes will not be recorded on the YouTube video. Just want to point out here, the sphere with more charges on it has more charge, right? Okay, so more plus signs, more charge. You're looking for the picture that gives the correct visual for the forces that are acting on each of the spheres. don't know if it's too hard to see or not, but all of those charges are positive, right? Whether there's 2 charges on the ones on the left-hand side or 6 charges on the ones on the right-hand side. Okay, I'm going to give you like 30 more seconds. Write down A, B, C, D, or E, and try to have like a justification or a why, even if it's, I'm guessing. All right. Try to lock it in. Go ahead and turn to your neighbors. Tell them what you picked and why. Go. All right. Don't forget to write down any different answers, right, if you've got them. And what do you do if it's the same? Just write an arrow, right? Or just say it's the same, whatever. Just don't spend too much time. Don't redo your work. Okay. So, by show of hands, how many say it's A? No takers? Good. What's wrong with A? The forces are in the same direction. Like the force on the charge 2 there, right, is pointing towards the other one. And what should positive charges, what should the force always be doing? Going outward, away, right, from each other, okay? The vector on the one on the right, the 6 charge one, right, that one looks like it's going like kind of in the right direction, like away, right, okay, but something wrong there. So what is C correct? No, because it's missing a force, isn't it? Okay, so we're down to B, D, and E. So how many say it's B? A few of you? Okay, that's all right. D? Some of you, and E? Oh, okay. Okay. That was almost an even split between B and E, with the minority coming in at D, right? Congratulations, those of you that answered D are correct. Huh? What? Mr. Balogh, this one has more charge, doesn't it? Yes. But the people that answered D remembered Newton's third law. No? 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 What's Newton's third law? When 2 objects interact, the forces between them are equal and opposite in direction. Can the one with more charge exert a bigger force on the other charge? If you push somebody what do? They fall over. They push back. Gravity's trying to pull me into the floor with about 180 pounds of force. The floor is pushing back on me with 180 pounds of force. How do I know? Because two objects are in contact, and whenever two objects interact with a force, the forces between them are equal in magnitude, opposite in direction. So in the case of D, these two vectors are the same length, and they have to be. When we write down Coulomb's law for a charge, it's the force that both charges experience, right? If one pushes on the other pushes back. So I did, see, trapped you, right? Led you, some of you. So those of you that got it right are sitting there all smug. I'll get you later, okay? Those of you that didn't get it right, what are you feeling? Erase 50 points, right? No, just take it, right? What are you going to learn from this? That Mr. Balogh is just a trickster. No. Yeah, that we can't just forget 2A, right? That since we're talking about forces, Newton's laws apply also. Again, I'm not going to, on an exam, specifically try to trick you about Newton's third law, right? But we have to just get over the misconception that, more charge equals more force. No, that's not what happens, right? Same thing goes with gravity. The Earth pulls on the moon. Does the moon pull on the Earth? Is that weaker, stronger, or the same? It's the same. Even though the masses are different, the force between them is the same. Okay, so what I'm going to do is we're going to do an example of dealing with Coulomb's law mathematically. How do we calculate with it? What do we do, Mr. Balogh? So what do we got here is we've got some charges. Now, so this charge number 1 is plus 2 microcoulombs. So when you see the word micro, what do you instantly think? 10 to the minus 6, right? Now, what's different about charge 2? It's a negative charge, right? And then the one down here, also a negative charge. They're all 1 meter sort of away from the origin. And so what we're going to do, okay, what is the problem asking us to find? We want just the force on this one. Well, based on the quiz we just did, right, okay, if we simply, we're just going to laser focus on charge 2 right here. Is charge 2 experiencing a force? Does Coulomb's law apply here? Do we have charges? Yes. Do we have 2 charges? Yes, we have more, right? Are those charges some distance apart from each other? Yes. So the answer is yes. There's very definitely force happening here, right? So we need to kind of compartmentalize, break down, really think sort of the physics that is going on here. And what I want to do right now is I just want to think about charge 1 and charge 2. Force is a vector, and so we can just look at the interaction between 2 charges, figure out that force, and then we can look at a separate interaction with another charge, figure out that force, and because it's forces, we can then add those forces together. You probably did this when you did, when you finally got to Newton's laws, or using Newton's second law and stuff like that, okay? So our plan of attack here, we're going to look at charge 2. We're going to try to determine what force is happening between charge 2 and charge 1. And then we're going to do the same thing between charge 2 and charge 3. And when that's all done, we're going to add it all together. So we know Coulomb's law is happening. We want to find the net or total force that's acting on these charges. And physicists in your book use a little notation here to try to mathematically spell out the idea that I just told you. We're going to find the force. okay, on, make sure I get it right for your book. I wrote this down earlier. Yeah. The force on charge 2 because of charge 1. That 2, 1 down there in the denominator, according to your book, and I'm going to get this backwards half the time because I learned a different method. But in your book, it's the force on the first number because of the second number. Does charge 2 experience a force because of charge 1? Does Coulomb's law exist? Yes, right? So that's what that sort of symbol right there is trying to encapsulate, right? And then we're going to add to that the force, the other interaction. So which charge are we trying to calculate the force on? 2. But where's the other force coming from? 3. So we're going to find the vector sum of those 2 individual forces. This is our overall plan of attack. It's part of the problem-solving method. We want to sit down, want to outline what we're going to do first before. Now, arguably math is on the screen, but have I done any math? No, I'm just kind of using the language of mathematics to spell out my plan of attack. But each of these forces right here, right, each of those is going to be an application of Coulomb's law. That's where the force is coming from. So if I'm going to calculate, say, F21, and I'm going to find its magnitude, the amount of force, the number that's associated with the force, then I have to use the electric force constant. I have to use charge 2, charge 1, right? It's 2, 1. And then I have to use the distance 2, 1 squared. See how I've kind of picked up some subscripts here to try and keep everything organized? Okay. Now we can go ahead and plug in some numbers. What's K? Does anybody remember? It's practically 9 times 10 to the 9. And I tend to drop the units when I do calculations because if everything's in standard units, then everything's going to come out in standard units. If you want to put the units in and make sure everything cancels, that's probably a safer thing to do. For the charge. Now, you'll notice what's sitting around these charges. It's the absolute value. So when you're calculating the number, does it matter what the sign is? No. Okay. So I'm going to put in for charge 2, I'm going to put in 4, but I'm not going to stop there. It's 4 microcoulombs. And what do you slot in for micro? 4 times 10 to the minus 6. And the reason it just went in as 4 and not negative 4 is because it's an absolute value. All right. What's the other charge? Charge 1. 2 times 10 to the minus 6, because it's also microcoulomb. So there's what the top's going to be. What's the distance? Ooh, okay. We need that distance right there, don't we? Distance between the charges. Yeah, now we've got to do some trig, don't we? Pythagorean theorem kind of stuff, right? So spoiler alert, this is a 45-degree angle, right? So this is the square root of 2. It's 1 squared plus 1 squared square rooted, right? 45, 45 triangle, I always remember the hypotenuse is root 2. Root 2 times whatever the length of one side of the triangle is. So I know that that's the square root of 2. So that's going to be the square root of 2 squared, right? And now all of that has to go in a calculator. I will save you the pain. I got 0.36. No, I got 0.036. I can't even read my own handwriting. There we go. Okay. 0.036 Newton. It's just a number, right? I calculated the strength of the force, right? Okay. Is the thing that I've written in red a vector? No. I mean, it's supposed to be, but is it? Can a vector ever be just a number? No, it has to have direction, right? We haven't done anything with the directions. Do you want to deal with direction right now, or do we want to just calculate the other one first? I don't care. Doesn't matter. Calculate the other one first? Let's just get the numbers out of the way. Okay. So what does the calculation look like for our other one, F23 here? I'll do it in blue. So F23. What would I write down? What's the first symbol I use? K. And then which charge? Q2, right? Just follow the subscripts. Q2 and then Q3 divided by the distance. Which distance? 2, 3 squared, right? Just trying to be careful about which distance we're talking about. Okay? Now I can put in some numbers. What's K? Okay, I admit I cheat sometimes and just write 9E9. Move on with my life. All right, Q2, what's Q2? Be careful. 4, good, times 10 to the minus 6. Always write out the full number. No, don't just put in 4 microcoulombs because who knows what you're going to end up with. Okay, and then what's charge 3? 6 microcoulombs. Remembering that we're not worried about the charge, the signs of the charge just yet. And then can you give me the distance, R23, the distance it's right here? It's also square root 2. It's the other sign. It just happens in this problem to be equal. Okay. And then we chuck that into a calculator. And that's what I got. Okay. So that is not what I got. It shouldn't. I know this is wrong. Why is this wrong?
It should be smaller.
It should be bigger. It's the same distance, but it's bigger charges, right? So it should be bigger, and indeed it is. I just read the wrong line on my sheet. 0.108. There we go. Newtons. Okay. So now I've got the magnitudes. We have to worry about direction now. So we're gonna pause the math part, like the do it part, and we are going to cycle back to the planning, the physics part, and see if we can't figure out what direction these things are acting. So let's look at F21, right? F21, that's the force on 2 because of charge 1. Charge 1's positive, charge 2 is negative. You know the rules. Opposites attract, right? So what direction would be the attraction, the pulling together? Right? It's that way. So I'm going to go ahead and I'm going to draw that. I'm going to say this is the force, right, on charge 2 because of charge 1. It's heading down in that direction. Now, don't draw this, but is there a force up here that's equal and opposite? Yes, but we're not calculating the force on charge 1, right? We're only calculating the force on charge 2. Don't do more work than you have to, okay? Okay, so that's F21. F23, they're both negative. So what's the rule? Opposites and likes repel, right? So which way would be repelling away from? People on YouTube will be so confused. Okay, so that right there is F23, isn't it? Now, can we just add these two numbers together and get the right answer? No, right? So the 0.036 is pointing at some angle down below into the third quadrant, isn't it? And the blue one, F23, is pointing up like into the second quadrant, isn't it? So now we have a vector problem. We have a problem where we need to add together, right, a force of 0.108 newtons acting at what angle? I said the angle before. It's 45 degrees. Okay? With another force that's acting down at 45 degrees but is smaller, 0.036 at 45 degrees below the axis. Okay. Since the majority of you took Dr. Kerfoot, we'll go with Dr. Kerfoot's method. How did he teach you how to do this? Did he use the angle from the positive x-axis? Or was it always an angle less than 90 degrees and you picked like positive and negative directions? Does anybody remember? So in other words, do we use 45 degrees or do we use 135 degrees? You use 45? It's because Dr. Kerfoot is my man. Oh, I love him. Okay, good. Because that's the better way to do it, right? Okay. So we're going to use 45 degrees and let's I don't know. Let's do F23 first. Okay. So we want to find both the y and x components. F23x, right? That's going to be 0.108, and then is it sine or cosine for the x component there? This component right here. Sine or cosine? You sure? Adjacent? Yeah? Uh-oh. Uh-oh. Okay. Dr. Kerfoot's not my man anymore because he didn't teach you the better way to do it. It's not his fault. He doesn't really know about it. This is definitely a Mr. Balogh thing. Ignore all that. I just needed a blank. So let's do it this way. Okay. Here is a hypotenuse, and we want to find the legs of this triangle. We want to find AX and AY. And here's the angle. Let me show you how to do this really quickly without having to think. Okay? If the side you are looking for touches the angle, it's cosine. What does that mean? It means that I find AX by using A cosine theta because the angle right here touches the side I am looking for. The angle always touches the hypotenuse, doesn't it? If you can't identify the hypotenuse of a triangle, I cannot help you. Right? What's the hypotenuse of a triangle? It's always the side that is the longest side. So as long as you can find the longest side, okay? And since in physics, most of our triangles are right triangles, if they're not, we make them be, right? Then it's always the side opposite the 90-degree angle, okay? But as long as you can identify the hypotenuse, then the side that touches the angle is cosine. Do you want to guess what the side that doesn't touch the angle is? And that's it. You don't have to do adjacent and co-adjacent or whatever that is. It's just touching, not touching. And this works really well, especially when you have situations, say, like this one. If the angle is right there, how are we going to find BX, sine or cosine? Sine. How did you know? It's not touching the angle. Yes, it's the opposite side, but that's what it means to not touch the angle. Did Dr. Kerfoot warn you that X isn't always cosine and sine isn't right? Okay, that's the reason being is because the angles can be specified from other places besides the horizontal. So what I do is I just do touching, not touching. This is something that I feel like I came up with. I'd never heard of this from any other students, any other teachers. When I realized it, I sat there for a while. I was like, this can't be right. This can't be true. There's got to be exceptions. I thought about it some more. I really just didn't want to do my math homework. So I just kept thinking about it. And I went to my math teachers in college and I said, does this work? Is it true? And at first, the teacher was like, well, no, this is stupid. And then he just kind of stopped and he went, well, let me see if I can think of a counter argument. And then he just kind of sat there for a little bit. And he just kind of looked at me. And a tear started to sort of drip down his face. And I knew that that's when I had to walk out, right? Because I had just destroyed a career. Trigonometry as a class doesn't need to exist anymore because all you need to know is touching, not touching, and you're done. Everything else, useless. Do you guys remember all those trig identities? Yeah, useless. Really, just really useless. There's one trig identity that we use constantly in physics. Cosine squared plus sine squared, square rooted equals 1. That one's really useful. Everything else, waste of time. You're welcome. I just told you all of trig in 5 minutes. Okay, back to this. Okay, so if we are going to find the x component of F23, does it touch the 45-degree angle? So what is it? It's cosine. I still have students every year write me that have transferred on and they're like, Mr. Balogh, I need to thank you for touching, not touching. Right? It's a weird subject line for an email, but I get what they're trying to say, right? Because they're like, I can do this so much faster than everybody else at my college did. Yeah. Okay. And then we would calculate that out. F23y. Sine or cosine? Well, we've already used cosine, so it better be sine. And it just turns out that because of the 45-degree angle, what's the number? It's the same. 0.025, 0.025. The sine and cosine are the same for 45-degree angle. Okay, so those are the values, right, of the components of the vector. Now we have to be really careful about the direction that these components are pointing. Is the x component pointed in the positive or negative x direction? It's in the negative direction, right? So I've got to remember, this is the one part where you do have to have a brain. You have to remember to go back and put a negative sign on it. Okay? What's the y component doing? It's going up. So that is a little bit of a price you have to pay. Okay, let's do F21x. So F21x, woo, come back here. F21x, right, is also pointed to the left here. Is it touching the 45-degree angle that's below the x-axis? Yeah, so sine or cosine? Cosine, so it's going to be 0.036 cosine 45. F21y is 0.036 sine 45. And I got, darn it, I keep writing down the wrong, oh my gosh. I need to be fired. I do. I just need to be fired. 0.025 is the answer for F21. This is, and is it, what direction is the x component pointing? Negative. What direction is the y component pointing? Also negative. I do need to come back over here. I am so sorry. You weren't supposed to be taking notes yourself anyway. You're supposed to be taking notes about how stupid Mr. Balogh is. This one is 0.076. Whoa. See, I have some dust I got to knock off after the summer too. All right. What do we do with all these numbers? F23x and F21x, they go together, don't they? We add all the x components together. We add all the y components together. And we get f, the resultant, just fy, okay? Fx, go x direction first. Okay, Mr. Balogh, read the correct one this time. I got negative 0.101 newtons, and for Fy, I got 0.051 newtons. So that means that the resultant force acting on charge number 2 points in the negative x direction and the positive y direction. So what quadrant does that get us in? Gets us in the second quadrant. So if I go find the magnitude of this, this isn't the magnitude yet, right? This is just the components. How do I find the total magnitude of this force? Pythagorean theorem, right? Square root of 0.101 squared plus 0.051 squared got me 0.113 newtons. There's the magnitude. And if I need to find the angle, does anybody remember the horrible inverse tangent? I have no tricks. I have no stupid touching, not touching to help you with tangent. Tangent's just broken. It's dumb. Okay, so you just have to like draw the picture and deal with it. The y component 0.051 over the negative 0.101 for the x component. This gives me a negative 26.8 degrees. But again, you have to know that this is pointing into like the second quadrant, right? Negative, when you get a negative degree out of the inverse tangent, it means that you are rotating clockwise around the coordinates. Okay? A positive angle for tangent means you're rotating counterclockwise. So the sign is a direction of rotation of an angle. Tangent always returns an angle that's measured from the x-axis. The only question is it the positive x-axis or the negative x-axis? And the only way to answer that one is to just draw the picture. And by draw the picture, I literally mean it's right here. You draw xy axis. You say, okay, my negative x component, positive y component. It's coming over here, right? It's over here in the second quadrant. So that means tangent gave me this angle right here. The negative 26 degree angle is sitting right there. It rotated me clockwise away from the horizontal. Where's the other place you can get a negative angle? Which quadrant? Fourth quadrant. You can get negative angle there also. Okay. Again, what does the negative mean? Rotating clockwise. The angle is drawn from the horizontal. Tangent always references the horizontal. It's just moving it clockwise. Okay. Positive angles end up being the first and third quadrants. And how do you know which quadrant you're in? Draw the picture. Or think about the signs on your components, right? There's no way around that one. It's just hard. And it's bad. All right. Is it safe to say that your brains have rebelled about 30 minutes ago? Right? This is a horrible screen. This is just awful. Not only is my handwriting bad, okay? But like the amount of physics that we just like reviewed from physics 2A, right? And threw together with all of the Coulomb's law stuff, right? It's horrific, okay? It's a really big punch to the gut. I've just hit you in the head with a 2x4, right? Second lecture of the entire semester, and it's not gonna be this all the time. Just part of the time. Because what we're gonna do now is we are going to strike out for some sanity. We're going to try and take what we just figured out. Again, Coulomb's law being the absolute truth about a majority of what we experience on a daily basis. Coulomb's law is the law. It's more influential than gravity and all those different kinds of things, okay? What circuit can I trip? Let me do this one. All right. If I blow up the building, class dismissed. Okay. So what we're going to talk about now comes from the mind of the genius that is Michael Faraday. And again, Michael Faraday, another old white dude. But this old white dude, more like you and me than you would imagine. I wish I had the time to tell you the story of Michael Faraday. And maybe a little bit later in the semester, there's a documentary I can show you about the life of Michael Faraday. But he, by all intents and purposes, was a normal human being. As normal as you can possibly get in the 18th century British Isles. Like, born dirt poor, very little education, but had a mind that you wouldn't believe when it came to being able to picture how the universe worked. It is very safe to say that the modern society that we know and love, at least on the technological basis, sprung from the mind of Michael Faraday. And he's probably somebody you've never heard of, right? You've heard of Einstein, right? Nuclear weapons, that's what we got from Einstein, right? But out of the mind of Michael Faraday came the basic physics that would show us how to make wireless internet work, how to make radio work and television communicate, like anything that's wireless, every electric motor, every electric generator, understanding how magnets work. People were playing around with all this, but it took Michael Faraday to bring the concept home. He actually couldn't do math. He was never formally schooled in mathematics, but he rose to the preeminent scientific position in the British Isles at the time based on his ability to do experiments and explain what was going on. I'll tell you more about him later. Let's get into why Michael Faraday is so amazing and the amazing thing he did in telling us about electric field by introducing you to this thing I call a Van de Graaff generator. I call it a Van de Graaff generator because that's what it is. It doesn't generate Van de Graaffs. Van de Graaff was the last name of the guy that kind of put it together the first time. What this is a static electricity generator. Okay? Let's back up. Static electricity is what we've been studying so far. How is it? What's the other kind of electricity? If it's not static, it's dynamic. Right? Okay? Static electricity means that we're actually not looking too closely at the charges in motion. We charge something up and then we look at it, right? Next chapter, we're going to get into what happens when the charges start moving. Okay, we'll do electrodynamics then. But what this thing does is it's got a belt in it, a rubber belt. You can't see it inside here, but there's a rubber roller at the top. On the bottom, there's a felt roller that it goes around. And then there's an electric motor that the only thing the electric motor does is it turns the belt, right? So mechanically, you know how it was rubbing the rods with the fur and stuff like that? Okay? This does that mechanical rubbing only 10 gazillion times per second, right? It can do it much better, much faster. It can build up the charge a lot better than I ever could, okay? And the reason I wanted it here is to show you something. And we'll play around with this a little bit in lab too when we get there, okay? This is Fluffy the Wonder Fur, remember that, right? Okay. I want to show you the electric field that exists around this dome when I charge it up. Watch this. Right? I don't have to touch it, but I can influence the electric field that exists around this dome, right? I can do different stuff with it. And if I'm not careful, I can pull shocks off of it, right? Okay? But I wanted you to see, right, the electric field and the fact that I can influence that field, right, by not touching the dome. What I'm doing is I'm putting another charged object in the field and thus changing the field, and that would cause the fur to go up and down. Like I said, we're going to play with this a lot more. Those of you that have long hair, I'm going to target you because we want to see your hair go. No, I won't make anybody touch it that doesn't want to. Okay? But we'll play with this in lab a little bit more. I can't remember if that's Monday or next Monday. But that electric field, okay, exists around every object that has net charge. So a neutral object, by definition, has no field around it because the net charge on that object is 0. But as soon as you charge something up, you put an excess of positive or negative charge on it, it's going to have electric field. Now, what the electric field does is it is an abstraction. It's an idea that takes us away from the complexity of Coulomb's law. Again, Coulomb's law being the fundamental universal law that governs all electric charges. And we take a step back from that and we say, okay, is there like an easier way, both mathematically and conceptually, to keep track of everything that's going on? I mean, you saw what happened when we just did 3 charges, right? How many charges were on that dome? Trillions of charges, right? Okay? Can you imagine having to track the vectors for all trillion charges interacting with each other? I mean, supercomputers can't even do that. So what the electric field is an attempt at describing what's going on in a manner that is conceptually easier to wrap our brains around, but also mathematically easier to deal with. And though Faraday would imagine this in his head, okay, others came along to give it the mathematical symbolism, right, that Faraday was talking about. So we'll start a little bit with the math and then we'll go into a little bit more of the picture, okay? So the electric field that exists around any object that has charge is equal to the force that charge is experiencing because there are other charges around it. Now, I know this looks a little bit weird, and we're actually not going to kind of use this thing in the box. This is the basic definition. And you're like, but Mr. Balogh, this has still got a force in it, and force, when it comes to electricity, is nasty. It's Coulomb's law. And I don't want to have to do one of those vector problems again, right? Nobody wants to do that kind of stuff. So that's the general, right? We can apply this no matter what the pattern of forces is in any collection of charges. But let's take a look at a specific case where we've got like a positive charge that just plunked down somewhere, okay? And then I'm going to put the test charge, this Q naught. It's the thing that's sitting down here in the denominator, okay? And we want to find the electric field that is surrounding this positive charge right here. This charge is giving a pattern of forces. That's what a field is. It's giving a pattern of forces around it. And if we take our little test charge and we move it to different places in this field, then we can establish what that pattern looks like. So let's say, for example, the test charge is where I pictured it right now. And by definition, the test charge is always positive. So I've got 2 positive charges here. What direction is the force right now on the test charge? Yeah, okay, so have you guys noticed that we've got a problem when it comes to talking about direction? If it's not on the X or Y axis, we kind of have to do this weird, right? Okay, in physics, we actually have a way of doing that in one word, with 2 words, but same idea. Those words are towards or away. What direction is the force acting here? Away. So the away direction would be that way, wouldn't it? Okay. What if I dropped the test charge down here? What direction is the force? Away. Away from that charge in the middle, right? What if I put it over here? Away. So if I asked you to describe the electric field around the dome of the Van de Graaff generator, right? Say we just charge it up with a bunch of positive charge, right? What direction would the electric field point everywhere? away from the dome, right? That captures, no matter where I am in space, right, the direction that it's going to be going. So that's one power of the electric field, to kind of simplify the description of what's going on. But if we really look at this and we say, okay, what's this electric field like? What's the number here, right? Well, it's the force, which would be Coulomb's law. K, and I'm going to call this one big Q right here, okay, times the test charge, Q naught, all divided by the distance between those two things squared, divided by Q naught. Remember, there's a little Q naught down here, right? We write the force. Here's the force via Coulomb's law. Divided by the test charge. Mathematically, what cancels? That's because it's all magic, right? What goes away? It's the Q naught. Boom, boom. And we're left with a statement that says the electric field of a point charge, PT, right? The electric field of a singular charge somewhere in space is K times Q divided by the distance squared from that point charge. Now look at it really closely. How many charges are in that statement? It's just one charge. And what charge is it? There were two charges, now there's one. Which one went away? The Q naught, right? The test charge. So what makes electric field? Is it the test charge? No. The thing that makes electric field is the charge we're talking about, right? We want to find the electric field around that positive charge? Then the only thing we need to know is the charge that's there. It doesn't matter what the test charge is. It can be as big or as small as we want it to be. We can go through, we could find, right, all the electric, but the electric field is caused by charge itself. And it's the only charge we really need to worry about. Now, of course, could I come along and say, okay, I want to know the force on this test charge? Yeah, I could do that. We go back and do Coulomb's law and like break our brains. Or we could find the electric field at this point in space. And if we know the electric field at that point in space, what do we do to find the force? We just multiply by the charge that's sitting at that point in the field and we're done. It's more elegant, it's faster, and the computations are a lot easier to do it that way, okay? So let's do you want this one at the end of today or do you want it at the beginning of Tuesday? Today? Get her out of the way? Okay, let's do quiz 18.5, 18.6. It actually didn't really matter. We could have gone either way. But let's see if I can get you mad at me. 18.5, 18.6. What I'll do on Tuesday... Okay, so I am not done with chapter 18. So I have already messed up the schedule, right? But that's okay. I think I don't need as much time in chapter 19 as they specify. So I might pick up the pace just a little bit when it comes to chapter 19. We're kind of almost done. I've got one more example to show you how to calculate the electric field, but that's okay. Your homework for chapter 18 is not due Saturday, right? It's due next Saturday, right? Past me had my back. Knew what was going to happen. Okay, so we got the 18.5, 18.6 down. Again, after today, the quizzes will be edited out. That was my reminder to stop the recording, but we'll let her go. This looks very familiar, doesn't it? Only this time, tell me the electric field vector. Not the force. I want the electric field vectors. And just for clarity, I'll use, okay, well, we know C is wrong, right? Okay, so if we're looking at C, right, then this arrow over here on the right is coming from the charge on the left. Does that make sense? So arrows on the left are coming from charges on the right. Arrows on the right are coming from charges on the left, right? I want you to pick the picture that is correct for the electric field from those charges. Let me help you out. It's not D. Not supposed to be talking. Okay, 30 seconds. This one, I'm hoping, is kind of obvious. All right, turn to your neighbors and decide which one it is. Go. All right, don't forget to write down any changes, group answer, that kind of thing. All right, how many of you say the answer is D? Good, you were listening. All right, we know the answers are not C and D. Is A correct or not? No, again, they're pointing in the... So we're back to B and E now, right, aren't we? Okay, so we've narrowed it down to that, okay? Both B and E are correct in one sense. There's kind of two things you have to think about here. You got to think about direction, but you also have to think about strength, right? Magnitude of the electric field. So where are B and E in agreement? With direction, right? Both of these vectors are heading away, aren't they? Which is correct for the electric field, isn't it? We just said positive charge has field that points away. Okay. But which one is correct in terms of magnitude? Which of these charges, the big charge or the small charge, creates more electric field? The big charge. Why is it the big charge? Electric field is KQ. Which charge? Whatever charge is making it, right? Not the one that's experiencing it. It doesn't matter what the charge experiencing it feels. Electric field is created because a charge exists. So if we want to look at the electric field from the charge on the left, it being the smaller charge, it's going to make the smaller what? Electric field vector. So which is more correct, B or E? It's E. The small charge makes a small electric field over here, right? What does the big charge do? Makes a big electric field over there. Does that mean giving you the same pictures? What's the mine there? What's the trap? What's the confusion, the electrical confusion between electric field and forces? Is the force and the electric field, are they the same thing? No. What's a force? Do I have to beat up Dr. Kerfoot now? It's a push or a pull. That's what a force is, right? Are electric fields pushes or pulls? They are a pattern of pushes and pulls, right? And so there's a difference there. They're both represented by vectors, aren't they? One is a push or a pull. That's the force. That's Coulomb's law. One is a pattern of push and pulls. That's the electric field. And if the charges were negative, what would happen to the direction of those vectors? They'd turn around. So negatively charged things, which way does the electric field go? Inwards, towards the charge, right? Positive, away or outwards. Negative, inwards or towards. We'll finish all that up on Tuesday, and I will see you hopefully in GRASP tomorrow if you want to get a jump on your homework, which will be an excellent idea. Otherwise, I'll see you Monday.